So the name of the talk is Algebraic Periods of Surface Homomorphisms.
Thank you. First of all, I would like to thank the organizers for their efforts to organize this meeting and for the possibility I can be here and give this talk. And I will be talking about the joint project with Grzegorz Graf and Adrian Myszkowski from Gdańsk University of Technology and with Wacław Marzantowicz from Adam Mickiewicz University in Poznań. And this is a project from, say, topological fixed point theory. So if we have a map, say for simplicity of a compact CW complex, yeah, it is natural to ask about fixed points of this map or about fixed points of iterations of this map. So a fixed point of some iteration Fn of a map F is called the periodic point. And we distinguish periodic points of the minimal period. So such fixed point X of some iteration of a map F, which are not fixed points of some smaller iteration of this map. And the set of all minimal periods of a map F, we denote by parallel of F. Yeah, and one of the main goals is to study this set of minimal periods of a map. So classical Lefschetz fixed point theory provides a description, sufficient condition when the map has a fixed point. So if the Lefschetz number of a map, which is just recall the alternating sum of traces of maps inducing homologic groups. So if this Lefschetz number is non-zero, then a map has a fixed point. So if the Lefschetz number of some iteration is non-zero, then F has a point, periodic point of some order n, but using this Lefschetz fixed point theorem, we don't know whether this period is minimal because X can be also K periodic for some K dividing n, or for example, it can be the fixed point of a map. So how to distinguish it? Here me is a classical Möbius function and sequence of Lefschetz numbers of iteration of a map F satisfies this quite known Dot condition, Dot congruence. So this sum over divisors of n, where we multiply the Lefschetz numbers of k iterations of F and the Möbius function of n over k. This number is divided by n. And this formula can be shown topologically, geometrically, but also there is quite elementary algebraic proof using some congruences of traces of matrices, integer matrices. But using this Dot condition, we can define the sequence AN of F. This is one over n of this congruence, and this is the numbers. And we can define the set of algebraic periods of the map F as the set of those indices n for which AN of S is non-zero. So these are algebraic periods of F, and they provide some information about the periodic of a map. So recall here is a classical inversion formula. So we have two number sequences, and one of them is described by the second one as the sum of those elements indexed by the divisors of n. We can inverse this equality and describe En as the sequence AN and using Möbius function. So in particular, this inversion of this is that the Lefschetz numbers of iterations of a map are described by algebraic variants in this form. And in particular, one can show, but it is not straightforward because it needs to use theory about prime numbers, that the Lefschetz sequence of iterations of the map F is bounded even only if the set of algebraic periods is finite. And in this talk, I will focus on this case where this set is finite, because then there are only to use algebraic methods, but if the sequence is unbounded, one can use some analytic methods to study properties of the sequence and periodic points of the map. Okay, so let us see on the elementary example. So if X is just a finite set, and if we have a map of this set, then on the only non-trivial homology is zero homology, and the trace of this map is just the sum, just the number of fixed points of a map. So the Lefschetz number of Fn is just the number of fixed points of n iteration of F. And so we use this Mobius inversion formula. The sequence A and F is just 1 over n, the number of periodic points of F of the minimal period n. So this number is non-zero even only if the set is non-zero. So the set of periodic points is just the set of algebraic periods. And in particular, we have important for us implication that if the algebraic period, if we have some algebraic periods, so if this element is non-zero for n, then we have a periodic point of minimal order n. But this is not the general case. There is, for example, the construction of Shoup of a map of the two-dimensional sphere, where each element an of F is non-zero. So the set of algebraic periods is just all the set of all natural numbers, but the fixed points of F and all its iterations are just 2 points, 2 poles of the sphere. So the periodic the minimal periods of F is just one element set, which is 1. So the question is, I will also mention for a moment about other motivations, but what are possible sets of algebraic periods of homeomorphisms, and in particular of surface homeomorphisms, and what are relations from the set of algebraic periods to what can be said about the set of minimal periods for some nice class of functions. And such important class of functions are transversal maps. So a smooth map of a manifold is transversal if each is a periodic point. For each periodic point, the differential of this iteration of a map has no one as an eigenvalue. This is one of the possible definition, equivalent definition of the transversal map. But this class of maps has, first of all, this is generic class, so any map can be arbitrarily approximated by transversal map. In fact, in the homotopy class, one can find always transversal map. Moreover, the set of periodic points is isolated. So for a compact manifold, there are finitely many periodic points. And what also can be shown, is known, that if an element an over is non-zero for a transversal map, so we have algebraic periods n, period n, then in fact it implies that there is indeed some periodic point of minimal order n for n odd number. Because if n is even, we have two possibilities. We have minimal period n or n divided by 2. So in this class, the study of this sequence AN of F and the set of algebraic periods provides also information about the set of minimal periods of the map. And of course, this sequence, because it is determined by the sequence of Lefschetz numbers, is a homotopy invariant of the map in the homotopy class. Okay, and very known and well-studied class of maps which are transversal are Morse-made diffeomorphisms. I will not go deeply into this the definition of Morse-made diffeomorphisms, but these are such diffeomorphisms for which all periodic points are hyperbolic, and there are finitely many of them because all of them are also so-called non-wandering. And there is also some condition for the stable and unstable intersection of stable and unstable sets of this map. Of course, such Morse-made diffeomorphism comes from the Morse-made flows on a manifold, but in our context, it is the description provided by Schuh of maps induced on homology groups by Morse-made diffeomorphism, and all these maps, it turns out, they are quasi-unipotent. It means that all eigenvalues of maps induced on homology groups are primitive roots of unity, are just roots of unity. So this is class of quasi-unipotent maps is the class we will say more for a moment. Okay, and our first motivation to start this project was were many papers about some mysterious object, the minimal set of Lefschetz periods of Morse-made diffeomorphisms. There were many papers of them. Here are just some examples. In fact, many of them are written by Libre and collaborations. So this set of minimal set of Lefschetz periods is described in some complicated way using zeta Lefschetz function and all possible representation of the zeta Lefschetz function. But what we showed that in general we have a map which sequence of Lefschetz numbers of iterations is bounded. So, for example, this is the case for Morse-made diffeomorphism. Then this set of minimal Lefschetz periods is just the odd algebraic periods of a map. So this is very easy description of the set, and it simplifies considerations. And in particular, it was known that this set of minimal Lefschetz periods, because it contains only odd algebraic periods, it says about the minimal periods of F. Yes, because for transversal maps, all odd algebraic periods provide a real periodic point of minimal period. Okay, and to describe, because in these papers there were many open questions about the descriptions of this set and Morse-made diffeomorphism, for example, for surfaces. So to describe it, we have, of course, description of mapping class group of a surface and famous Nielsen-Ferguson classification of surface homeomorphism. So in general, surface homeomorphisms are...
I'm sorry to interrupt you, but you have only 5 minutes left.
Yeah, I know, thank you.
Okay.
We have partition of the three classes: periodic homeomorphism, reducible homeomorphism. So we can cut a surface into parts, and on each part there is some power of this map, which is a cell map of this piece of the surface, and the class of pseudo-Anosov maps. But the class of reducible homeomorphisms can be divided into two parts, T2 and T3, and one T2 contains only those reducible homeomorphisms for which these self-homomorphisms of pieces after cutting the surface are periodic. This is the class of algebraically finite type. And T3 contains such reducible homomorphisms where at least one part is pseudo-anosy. But it turns out that almost 40 years ago, Daroha described homotopy classes of Morse-made homomorphisms, and these are exactly classes of type T1 and T2, so the classes of algebraically finite type. But also these results were recently repeated by Greenes, Morozov, and Kuchinka for orientable surfaces. Okay, so yeah, here are equivalent conditions for a homomorphism of the surface. This sequence of lashless number is bounded. We have finitely many algebraic periods, and the second condition, this map induced on homologic group is quasi-unipotent. So this is quasi-unipotent. And Nielsen, in one of his papers about the surface homeomorphism, conjectured that this class of algebraically finite homomorphisms of algebraically finite type are the only classes which are quasi-unipotent, whose map induced on homology groups contains only the spectra are only consist of roots of unity. But the first construction of pseudo-anosy map problem is, for example, example of a map which induces identity on the homology group. So this is quasi-potent, but this is pseudo-anosy, not of algebraically finite. But there is still question whether each quasi-unipotent map can be realized by a homomorphism of algebraically finite type in these two classes T1 and T2, so by a Morse-made homomorphism. So for now we just I have 2 minutes. We provided a construction of Morse-made homomorphism whose set of algebraic periods is a given finite subset of natural numbers A. And so this is a map of algebraically finite type, so it can be taken to be Morse-made homomorphism. And the genus of this map can be more or less equal to the sum of this algebraic periods, given algebraic periods. So this sum is equal to G, and the number of partitions of the G is, you see, was of course well studied, and asymptotically this is the following formula. And because this set is a homotopy invariant, set of algebraic periods is a homotopy invariant, so we have this number is the asymptotic, at least asymptotic lower bound for the number of homotopy classes of Morse-made homomorphisms of the surface. I think I will finish in this moment. So, okay, thank you.
Thank you very much for your talk. I think there is much more information in your papers.